So let's talk a little bit more about the types of liquid chromatography now. So I've given you the basics. So definitions and why peak shape's important and why resolution's important. And that's, you know, that was the first chromatography course I took in a nutshell for you guys. In about 20 minutes, I just explained a whole year's worth of chromatography when I was an undergrad. My second chromatography course was all about this stuff. So the types of absorption that you can play with in order to get different types of separation. So I would say the most common that everyone's heard of is reversed phase chromatography. But it's hard to talk about reverse phase chromatography without first talking about normal phase chromatography. Both of these are a type of adsorption chromatography. So the idea here is that you've got a stationary phase that is an opposite polarity to the solvent running through, and you're just relying on weak adsorption, adsorption interactions, not absorption. It's not holes that it's necessarily going into, it's just interacting with the stationary phase. Size exclusion has a little bit more of an absorption with the B concept going on here. So usually with size exclusion, we're talking about something like gel permeation chromatography, and we're definitely trying to trap smaller molecules in the gel or the stationary phase and have larger molecules move through first. And this is even similar to gel electrophoresis, really. It's just sort of done in a column way. I remember doing size exclusion chromatography with gels in these glass tubes when I was an undergrad, and it was actually like one of the most memorable and fun labs I've ever done. I don't know why I liked it so much, but to get the gels out of the tubes, we had to take a little syringe and insert some buffer, and they would just like flew across the room. It was just, I guess that's why it's so memorable, because it was just like, you know, 30 people in their 20s laughing their asses off with these little, like, I don't know, jelly-like tubes were flying across the room. Anyway, on to the next one, partition chromatography. So there's two different types of partition chromatography that you'll have probably heard of, or that are pretty common now. Thin layer chromatography, one of the oldest chromatographies, and almost every single one of us has done this one, I'm sure, when we separated, what are they called? Why am I not thinking? Pigments from leaves on paper. I hope everyone's done this. So that's what we call thin layer chromatography. It can be much more sophisticated, where you have special absorbents on glass. And I know that JP's lab does a fair bit of thin layer chromatography as well. And this is a type of partition chromatography where the solutes partition onto a nonpolar or polar coating, and you kind of, they're just sort of there in a layer and they stick. They actually don't necessarily come off the layer. They stick to the layer and stay there. So you're not necessarily going to have a detector at the end of this measuring the way a mass spec. This won't work for a mass spec, but you could have like a visual detector. So you can take pictures, you can have fluorescent tags and things like that. And then as well, a new sort of cool, I would almost think of HILIC. HILIC is partition chromatography. It's like thin layer chromatography, but it does involve a bit of chemistry that's a little more sophisticated, and it happens in a column. So I love HILIC. We'll talk more about that later. I'll explain it in a little more detail. And then the final type of chromatography that's pretty common is ion exchange chromatography. So this is literally just taking advantage of cations and anions and the fact that positives and negatives charges like to attract to each other or repel each other, and using those different properties. So here you're usually changing the pH of your solvent as you're running your gradient. Oh, sorry, there's a fifth one. I forgot. Bioaffinity chromatography. I don't do much of this, but this is where people take maybe an antibody or some sort of binding ligand that has a very specific sort of biological or biochemistry to it, and you intentionally grab out something that's going to bind to that. So like I said, it's usually an antibody and sort of like an immunochromatography. Not always. So just to compare all these types of liquid chromatography that I just told you about, and sort of a table format, you could I'm going to make all these slides available to everybody too. I already have them available actually on our Google Drive. So if you want copies of the slides, I can always send them to you. But this little table here is a nice quick reference. So the chemistry that you're using for reverse phase chromatography is absorption and hydrophobicity. And the stationary phases that are most commonly used are C18, which is a chain of 18 carbons, or C8, which is a chain of 8 carbons, with just usually hydrogens and nothing else. And then your mobile phase can be many different things, many polar types of solvents like water, acetonitrile, methanol, buffers, and ion pairing reagents. And the ideal analyte that you want to separate on a reverse phase column would be larger non-polar or lipophilic analytes. You want things that are going to stick to the column that you can then pull off by changing your mobile phase chemistry. And so examples would be most organic molecules, so many metabolites, many synthesized organics and contaminants or drugs, proteins, peptides, lipids, and polyaromatics. So for those of us who do contaminant work, PAHs are well separated on C18 columns. Normal phase chromatography isn't used much anymore, although I've seen people kind of pulling it back out of the history books. This was one of the very first types of liquid chromatography that happened in a column where you had high pressure. And so usually when you learn chromatography in a course, they start out by teaching you normal phase and then sort of move you from there. But I don't see the point in teaching that way because it's just confusing. But here is almost the opposite to reverse phase. So here we're doing absorption chromatography, but the chemistry is based on hydrophilicity instead of hydrophobicity. And usually the stationary phase is silica or alumina. It's almost like inert. It doesn't have a lot of reactivity. Or if anything, it's a little bit polar, in fact. And then you are running a non-polar mobile phase through the column. Normal phase chromatography usually doesn't have a lot of gradients going on. It's usually just an isocratic run. It's very good for things like fats and oils, even though you would think that it should be polars. That's not actually what normal phase is good at. So I think the reason why I've seen more people using normal phase is because I've been doing more lipidomics. So more people who are doing lipidomics actually pull out normal phase columns. And I don't have a lot of other examples. So here I say no idea, but fats and oils. Most people still do lipids on C18. All right, so ion exchange. These are, again, based on charges. The stationary phase is usually an ionic group on a silica column, so maybe like an amine or an acid, a carboxylic acid style stationary or R group hanging off these silicas. And then your mobile phases are going to be pH dependent, and you're going to have to be very careful to make sure that you really understand the pHs and the chemistries used for these mobile phases because you're mixing acids and bases. Do not mix those. Don't do that. You either use an acid and dilute it or a base. You do not mix together usually, but be careful. And then there's charged compounds usually that you're trying to separate. So if you have a mixture full of charged molecules, ions, definitely consider ion exchange. If you're not caring about any other kind of chemistry, these ion exchange columns are usually really efficient and they give you really beautiful peaks. So some examples would be metal ions. Peptides are also ionic. We call them Zwitter ions because they can be positive or negative. Same with amino acids, nucleic acids, and organic acids. So honestly, ion exchange columns are really good for oligos as well. And then there's the Hillock, my new favorite. This is partition chromatography based on hydrophobicity. You can get multiple functionalities. You can get stationary phases with cations and anions or just sort of a C18 mix-up. There's water and buffers and acetonitrile can run through these columns, so very similar to C18 columns that way. Some people call Hillock reverse normal phase instead of reverse phase. I'm not sure why, but here you're usually separating small polar organics. So the reason why I'm loving Hillock so much is because if you notice, most of these are not ideal for small polar organics. Like you can use ion exchange for charge compounds, but what if there's no charge, but it's small and highly polar? Well, it's not going to stick to your reverse phase column or your normal phase column. It's just going to run straight out almost with the dead volume. Really, really difficult to get a peak shape and a quantification with a small polar organic. Hillock is ideal for that. So what kinds of things are we measuring? TCA and glycolysis, citric acid cycle, metabolites, and acids, amino acids, and you can use these for oligos, I've found. And I keep bringing up oligos for anyone who doesn't know. We've got a researcher here, JP Desaunier, who does oligos, and I know at least one of his students is here. So oligonucleotides are being run on our system right now, and I'm really trying to push you guys to try Hillock because I think it'll work really well. And then finally, we have affinity chromatography. This one is usually very specific to the ligand that you want to separate out, or sorry, not the ligand, the analyte. So the stationary phase can be many things. It's usually a biomolecule, and you're usually only running water or buffers through these kinds of columns, and you could be looking for anything. So you can do substrate enzyme interactions, antibody antigen, lectin polysaccharides, DNA, cDNA, hormones, receptors, advidin, biotin, glutathione and GST fusion proteins, metal ions, and polyhis fusion proteins. So in fact, this is really great for biomolecules as well, but you usually have to really understand what you're looking for. And then this would be for like purifying and really getting what you want in a complex mixture. All right. So, if I can't finish up by 11, I'll just carry on where I left off next week. So let's talk a little more about reverse phase. I've gone on and on. You probably feel like you already know more than you want to know about reverse phase chromatography. Oh, well, there's more to know. So this is just a nice visual for what this sort of looks like. So you have an aqueous mobile phase, you have a nonpolar solid phase, and over time, you're starting with this aqueous mobile phase, you increase the organic mobile phase, and the analyte that is nonpolar and wants to stick to the hydrophobic stationary phase comes off in the mobile phase. Usually we use these very short columns that have C18 groups on them with a very small particle size for our peptides and proteomics. So this is what's on our instrument right now and is running some of Sarah's samples. But we use a longer C18 column with a smaller pore size to resolve our nonpolar metabolites like lipids, neurotransmitters, and cortisol and other hormones. So this is the kind of column that we like for those. Another view of reverse phase chromatography. Remember I mentioned that, and this wouldn't just be reverse phase, but it's kind of cool. You can kind of think of these particles being coated, and this is a 2D slice. So in 3 dimensions, they kind of look like pom-poms or like, I don't know, micelles. And the polar molecules are just going to wash straight through. The nonpolar ones are going to get a little bit stuck, so they're going to have a longer retention time. And yeah, anyway, that's it. So you can sort of see the path of resistance here for the analyte when it's more polar versus nonpolar. Another way to look at a reverse phase chromatography is to think about its gradient and how it elutes. And very typically, you start out with a bit of a isocratic start. You usually use the same percentages when you start of mobile phase as you've dissolved your analyte in. So if you've dissolved your analyte in 5% acetonitrile, 95% water, you want to start out with that exact same percentage of solvent to polar or water. And then you hold for a bit. And the hold is actually waiting for that dead volume. You want to make sure that the dead volumes come through your column and that your analyte's going to stick at the right concentration. And then once you're pretty certain you've got everything stuck to your column, you start ramping up your concentration of organic. And you want to make sure that any unbound molecules, even though they've gotten on your column, actually elute before you start this gradient. Or you can start getting peak broadening and weird peak shapes. And then usually you hold at the top again at a sort of high organic to make sure you wash anything that's really stuck to the column off. And then a quick drop back down to your starting conditions, and you give some time to let your column do what we call re-equilibrate. So you want all of those C18 groups that are, sticking straight out of your particle like a pom-pom. As this gradient changes, they actually start changing their shape. So you want them to go back to their original shape, and you need to give them time to do that. Okay. Now Hillock. Another visual on Hillock, which is really cool. As this is like, it's partition chemistry, but it's not like TLC with a solid phase and a liquid phase, it's actually a partitioning between two solvents. So in Hillock, you've got a stationary phase that attracts water. And so you can think of your stationary phase as being something that's polar, coated in water or aqueous solvent. And then you run your nonpolar mobile phase through, and your molecules, your analytes, are going to pick between this thin layer of water on the particles versus your higher organic mobile phase. So usually this is happening on sort of an inert solid phase, and it takes advantage of some coulombic and or hydrogen donor interactions. So if you're really into chemistry, that might make sense to you, but if not, you can just think of it as like attracts like, and it's very similar to C18. Like I said, sort of mixed with normal phase and partitioning. It's a little bit of everything. So here you've got your Hillock phase. It's a little bit hydrophilic. You've got this thin layer of water. You've got an organic mobile phase. Your polar substance, if it's polar, is going to want to stay in the thin layer of water until you increase the aqueous concentration in your mobile phase, and then your polar substance will come straight off. And again, it's kind of dissolved. It's not actually sticking or binding. It's sort of dissolved in this thin water layer, which I think is really cool. All right. So this is what we've been using to separate our smaller polar and acidic metabolites. So we've been using Hillock columns for amino acids. I mean, it's actually still quite challenging to run these with this column with TCA cycle acids. I think I might need a smaller particle size and a slightly different gradient for those. So we're working on that. And you also have to play with the pH of your buffers for those. So we got a few of the TCA cycle, citric acid cycle kind of molecules, but a couple of them just come off in the dead volume still. Working on it. Okay, so I think I mentioned that there's a lot of different functionalities that can happen in a Hillock column. So you can actually have an amide, a diol, sort of mixed mode anion exchange or cation exchange, as well as mixed mode polars, and even zwitterionic columns. I have this circled because right now we're using a zwitterionic column to separate our amino acids. Is working pretty well, but I'm thinking I might actually move to something that's going to exchange cations or anions even for the citric acid cycle metabolites. All right. So we also run this zwitterionic column. We can run a high pH or a low pH through it, and we do, and that gives us totally different options. It's like the one column can work as a cation exchange or an anion exchange, which is another reason why I love this Hillock column. All right, so you can think of Hillock as kind of the opposite to reverse phase chromatography. You start with a high, and I don't know why this is UV absorbance. That's just the detector that I stole this from someone else's book or website, and they have a UV detector, so ignore this. But you start with a high concentration of nonpolar, and you hold. It's the same thing here. You want to make sure all your nonpolars and polars are retained. And then you start reducing your organic content, and you go to a pretty high water content. And this is going to help make sure that anything that was really preferring the polar thin layer of water comes out off your column. And then you do a quick change and re-equilibrate. You want to make sure if you're using any salts in your buffer that you give it a little bit of time to desalt as well.